All right, now that we've kind of had an introduction to vectors, one of the things you can use a vector for, really good use, is called dot products. Now in vectors, there's two types of multiplication. There's a dot product and a cross product, and they're called that by the two symbols, right? Don't we have two symbols for multiplying? Like if it says, for u times v, if you put a dot between them, that means to multiply. You could also, and later on you could also use an x for multiplication. So they just named the two types of multiplication by those symbols. So if you want to multiply one way, it's called u dot v. You don't say u times v. You say u dot v. Later we'll do u cross v. They're two entirely different things. U dot v is the simplest one. If I have my two vectors like this in component form, a1, b1, a2, b2, all you do for u dot v is you multiply the two a's together, so a1, a2, you multiply the two b's together, b1 times b2, and then you add those two things together. So you multiply the a's, you multiply the b's, and add them together. That's it. So like on this one right here, it asks you to find u dot v. So for u dot v, we're going to take 2 times 4 plus 5 times negative 3. So let's see, 2 times 4 is 8. 5 times negative 3 is a negative 15. So u dot v is a negative 7. That's it for dot product. That's all you have to do. If I had this one in ij form, same thing for u dot v. Remember, this is like 2 comma 1. This is like 5 comma negative 6. So you multiply the i's together, only don't put the i's with it, just the coefficients. So that's 2 times 5 plus 1 times negative 6. So that'd be 10 plus a negative 6. So u dot v is 4. That's how you do a dot product. One of the things a dot product is useful for is you can use it to find the angle between two vectors. If you want the angle between two vectors, the cosine of theta equals, on top, you take u dot v. So that's the dot product like we just did. On the bottom, we're going to multiply the two magnitudes together. So to find the angle between two vectors, we need the dot product of the two vectors, and we need the magnitude of each one of them. So like if we were going back to this one, okay, I want to know the angle between u and v. Well, we already know the dot product is negative 7. Let's find the magnitude of u. Remember, magnitude, we take the square root of a squared plus b squared. So here that's what? The square root of 29. For the magnitude of v, we take the square root of 4 squared plus negative 3 squared. That'd be 16 plus 9 is 25, so that's just 5. So now using our formula, it says we're going to take the cosine of theta equals the dot product, which is negative 7. On the bottom, we multiply the two magnitudes together. So square root of 29 times 5. So we're going to do that on our calculator and then do inverse cosine. So on your calculator for that, we're going to take negative 7 divided by parentheses the square root of 29 times 5. So I get that decimal. Now I want to take the inverse cosine of that answer. And I get 105.068. So theta equals 105. Can't see that very good. 105.068 degrees. Same with this one down here. We already have u dot v. We need the magnitude of u. So that'd be the square root of 2 squared plus 1 squared, square root of 5. Magnitude of v is the square root of 5 squared plus negative 6 squared. So 25 plus 36, square root of 61. So the cosine of theta equals u dot v, which is 4, divided by the two magnitudes, radical 5 and radical 61. Again, we would multiply that on our calculator. So 4 divided by the square root of 5 divided by the square root of 61. So I get that decimal. Now I take the inverse cosine of that answer, and I get 76.759 degrees. Okay, so we just found the three things we need and plugged it into the formula. Some other things here. A term from vectors is called orthogonal. Orthogonal is really very similar to perpendicular, except they don't have to be in the same plane. The definition of perpendicular means that they're two lines who are at right angles, but in the same plane. Well, vectors, if you run, they don't have to be in the same plane for this. I could show you, but if you can see, like here, these two vectors, you can see that, like here, these two vectors would be parallel because they're in the same plane. Well, what if I move this one above it like this? Well, now they're not in the same plane, but they're still basically perpendicular to one another, so that would be orthogonal. So same plane would be like this when they're actually in, you can put them both on the piece of paper. That's perpendicular. Orthogonal if one of them is above the other one like that, so they're not in the same plane. That's orthogonal. Well, they're orthogonal if the dot product equals 0. They're parallel, I have that down here, they're parallel if one of them is a multiple of the other one. So if you can take one of the vectors and do scalar multiplication and it equals the other vector, then they're parallel. Like these two, if I want to see if they're orthogonal or parallel, well, for orthogonal, I'm going to take u dot v. So that'll be -1 times 2 plus 4 times -8. Well, that's -2 plus -32, -34. So they're not orthogonal. Well, parallel, notice if I divide here, like if I take v divided by u, so 2 divided by -1 is -2, -8 divided by 4 is -2. If you get the same thing both times, these are parallel. Because what that means is if I took u times a -2, I would get v. So if I multiply one of them by a scalar and get the other one, they're parallel. Or this one, if I want to take u dot v, that would be 2 times -1 plus 1 times 2. Well, that's -2 plus 2 is 0. Since the dot product is 0, these two are orthogonal. All right. Another thing is this one right here is the component of u along v. This is kind of a tricky term, but it means how much of vector u is part of vector v. To find that, you take u dot v, so the dot product of the two, divided by the magnitude of the first one they give you. The component of u, you put the magnitude of u on the bottom. So all that means, like if this one, find the component of u along v. We're going to take u dot v, which is 1 times -2 plus 4 times 1. Well, that's -2 plus 4 is 2. Now we need the magnitude of u. Well, that's going to be the square root of 1 squared plus 4 squared is the square root of 17. So the magnitude of u, the component of u along v is 2 over the square root of 17. Because we just plugged into that formula, u dot v over the magnitude of u. Okay? It's a very technical thing. If you were using that in a physics problem, they would go through exactly what that means. Another use for dot products is, if you've seen this in physics, work equals force times distance. And that's, if you think of these, if these are both vectors, that's a dot product. So like here, the wagon is being pulled by a handle of 60 degrees from horizontal with a force of 20 pounds. So here's my wagon here. I'm pulling at an angle of 60 degrees from horizontal. So that's 60 degrees with a force of 20 pounds. Find the work in moving that wagon. So we're going to move that wagon 100 feet. Again, a term you'll get comfortable with in physics, work equals force times distance. Well, first, we need to write these as a vector. Well, our force is our pulling on the wagon. Well, in component form, if you remember our component form, it's the magnitude times the cosine of theta and the magnitude times the sine of theta. So the horizontal component, so how much of our force is pulling the wagon horizontally is 20 cosine 60. The amount of, because we're at an angle, part of our force is actually pulling up on that wagon a little bit, makes it easier to roll. That's the magnitude times the sine of theta. So that's our force vector. Now our distance vector, well, we're only going horizontally. We're going 100 feet. Since we're going horizontal, our angle is 0. So for our vertical, that'd be 100 sine of 0. Well, we're going to add those together. So this 20 cosine 60, again, if you remember your trig, you could just do that on our calculator. But that's to add those together. We're going to take 20 cosine 60, which is 20. You see, the cosine of 60 is a half. So that's actually 10. So our force vector is actually 10. The sine of 60 is radical 3 over 2, so that's 10 radical 3. Our distance, well, the cosine of 0 is 1, so that's 100. The sine of 0 is 0. So the dot product, we take force times distance, that'd be 10 times 100 plus 10 radical 3 times 0. Again, dot product, 10 times 100, 10 radical 3 times 0. Well, 10 times 100 is 1,000. Now here we're moving it, we're using pounds and feet, so it's called a foot-pound. Which you don't see very often, but that's like the American unit, be foot-pounds. But you write each one of them as a vector in component form, and then just add, and then just do the dot product. Or here you see these ramp problems a lot in physics. Here I have a cart on a ramp, so here's what we have here. We have a ramp. There's a cart sitting on this ramp. The cart weighs 200 pounds. The ramp is 30 degrees. There are three vectors three forces acting up. First, there's the weight of the box going straight down. Then there's a force holding it perpendicular to the ramp. So this is the force perpendicular. And then there's the force making it roll down the ramp. That's the force parallel. You can do these different ways. You can actually do these using trig. These two triangles, this whole big triangle, the ramp, and the small triangle inside, those are similar triangles. If you remember that from geometry, similar means their angles are the same, their sides are in proportion. So if the angle of the ramp is 30, this little angle right up here at the top, that's also 30. Well, the force of gravity always pulls straight down. So that 200 is going straight down right here. The force parallel, that's the force making it roll down the ramp. The force perpendicular is the force holding it to the ramp. So what force is required to keep the cart from rolling down the ramp? Well, that would be how much would it take to oppose this side right here? If this is what making us roll down the ramp, let's find what that force is right there. Well, looking at our picture, that if that's going straight down, our hypotenuse is 200. So from that angle, we want to find that the force parallel is opposite. The hypotenuse is 200. So that sounds like sine. So we'd say the sine of 30 degrees equals opposite, which is force parallel that we want to find, over the hypotenuse, which is 200. So our force parallel is 200 sine of 30. Well, the sine of 30 is a half, so that's 100 pounds. So you would have to push up on that ramp with 100 pounds of force to keep it from rolling down the ramp. There's another way to do it with just vectors, but a lot of times these can be done drawing a triangle. If you did that in physics, there's a formula for that, because we can actually figure out the formula actually just came from trig. So we just have to remember the force of gravity always goes straight down, so that's going to be the hypotenuse. The force to keep it rolling down the ramp is this side that's parallel to the ramp. The force normal, that's called the normal force. Normal means a lot like perpendicular. The force normal is what's perpendicular to the ramp. And that is dot products.